Hi, everybody. Welcome to another SPY review session. Today, we're going to be covering lab interpretation and calculations. My name is Ryan Feldman. I'm one of the emergency medicine pharmacists and clinical toxicologists with Wisconsin Poison Center. So, objectives, we're going to review the interpretation of arterial and a little bit of venous blood gases, review anion and osmolar gaps and their uses and limitations in toxicology, and then review and practice various calculations. We're going to start off with discussing arterial blood gases. Below, I have the components of an ABG listed. They typically will tell you your pH, which is your overall acid base status, a low pH being less than 7.35, representing acidemia or acid in the blood, and a high pH greater than 7.45, representing alkalemia or too little acid in the blood. PaCO2 is the next thing you're going to find on there, which is your partial pressure of carbon dioxide. And this reflects the amount of carbon dioxide your lungs have left in the blood. A high partial pressure of carbon dioxide means you're not breathing very much. It's often called a respiratory acidosis. And a low partial pressure of carbon dioxide means you're breathing a lot. You're blowing off a lot of CO2. It's called a respiratory alkalosis. A bicarb on an arterial blood gas is in reference to is actually a calculated value on an arterial blood gas. It's the amount of bicarb that must be present given the amount of carbon dioxide and the pH. But largely, this is a reflection of if you have a low bicarb, it's probably a metabolic acidosis, high bicarb, metabolic alkalosis. But we'll talk more about that. Then we have your partial pressure of oxygen, which is the measure of oxygen dissolved in the blood. This is the true thing that actually oxygenates all your cells. Even though we usually use a pulse ox, we're just using that as a surrogate for how much oxygen is dissolved in the blood. And this helps us assess oxygenation. If you have a low partial pressure of oxygen, it means you're not getting a lot of oxygen into the blood, and that's what we call hypoxemia. Then we have your SaO2. So this is actually the saturation of your hemoglobin. So it's the percent of hemoglobin saturated with oxygen. The higher your partial pressure of oxygen, the more hemoglobin that is saturated with oxygen. But it doesn't always correlate. It's actually kind of useful if we have a finger pulse oximeter that's showing 85% oxygenation, but our PaO2 shows very high oxygen. We know that there's actually something wrong probably with the pulse ox because we have enough oxygen in our blood. And this can help us identify heme poisons like methemoglobinemia. So we also have VBGs. These are very similar to an ABG, except your pH is going to be a little bit lower because you have more carbon dioxide in your venous system. So you could still use it to assess acid status. You just need to correct for the fact that it's a little bit lower than arterial. And then your venous partial pressure of carbon dioxide is going to be a little bit higher because you have more metabolic breakdown going on there. So 40 to 50 is normal there. And then your oxygenation in your tissue, well, you shouldn't have much venous oxygen. So it's actually a better measure of oxygen extraction. If you have a ton of oxygen in your venous oxygen, it means your tissues are not extracting it well. But you cannot use this to assess hypoxemia because you expect it to be low. And so overall, we use our pH, our PaCO2, and our bicarb to help us assess acid base status. And we can use on the ABG only some of these parameters like our partial pressure of oxygen to help determine whether or not our pulse ox is truly representing how much oxygen is in our blood. And this can be useful for identifying what's called a saturation gap, which is where you have, say, a normal amount of oxygen in the blood, but an unexpectedly low oxygen saturation on a pulse ox, which might actually indicate methemoglobinemia. You'll hear more about those in specific lectures about carbon monoxide or methemoglobinemia. So I'm actually not going to get too into it here. I just wanted to let you know that's another use for the ABG. Now that we've gone over the components of an ABG, let's see how we can use them to classify what's going on in your patient. I'm going to teach you a really ultra quick guide to acid-base classification, and it involves making this table here on the right. You take your components, which are the pH, CO2, and bicarb. These are the three things that we tend to use. You're actually only going to use the pH and CO2 from the ABG. The bicarb you want to use from your basic metabolic panel. Because remember, the ABG bicarbonate is calculated. It doesn't represent the actual measured value. So using a basic metabolic panel bicarb will help me classify acid-base status. So you take those three components and you classify them as acid, normal, or base. And I'll show you exactly how we do that. Let's use an example. Here's a patient with a pH of 7.28. Well, my normal range is 735 to 745. That's low, so I know low pH means acidic. Now, let's look at their respiratory component, CO2. Well, their carbon dioxide is 60. Carbon dioxide is an acid. Thus, having too much acid, the normal is 35 to 45, the same as the last two digits of your pH. 60 is too high. That's an acid. So I have a respiratory, carbon dioxide induced acidosis. And I might have some other stuff going on too. Let's check a look at our BMP bicarb. I see it's 26. That is normal. So in this case, it is a pure respiratory acidosis. And what's really easy is look where your check mark is. Is it an acid or a base? Then look what else is lining up in that same column. In this case, it's CO2. So I know it's a respiratory acid because I have respiratory acidosis and an overall acidosis. So we'd classify this as a respiratory acidosis. This is what you would see in somebody who has apnea or hypoventilation from, say, an opioid overdose, where they're not breathing, so they're holding on to CO2. Let's look at another example. In this case, the person's pH is 7.36. Now, true normal is 7.4. So while this isn't super acidic, it's still below normal. So I'll say it's an acid. Now, their PaCO2 is 60. That is too much CO2 again, and CO2 is an acid. So we are going to put that in the acid category. I know this person has a respiratory acidosis going on. However, in this case, their bicarbonate is 34. Well, bicarbonate is a base. My normal range is 22 to 28. So having too much of a base is basic. In this case, I have an acidosis, and it looks like it's a respiratory acidosis with a metabolic alkalosis on top of it. This is the kind of thing you would see in a COPD patient who has long-standing respiratory acidosis, so the body is compensated metabolically and has started to generate more bicarbonate. Let's look at some more examples. In this case, my pH is 7.52. That is higher than my normal range, and a high pH is basic. So I'll put that as a base. My PaCO2 is 28. My lungs are blowing off a lot of carbon dioxide. I have too little acid. My normal range is 35 to 45. I'm at 28. Having too little acid is basic. And my bicarb is actually normal. This is a pure respiratory alkalosis. You might see this in somebody who is hyperventilating, blowing in and out really fast, blowing off a lot of CO2. But they've only been doing it for a little while, so their body hasn't adapted at all. A patient with a pH of 7.2, well, that is below 7.35. That's acidic. A PaCO2 of 40, that actually appears to be normal. And a bicarb of 14. Well, in this case, I know I'm overall acidic, and my bicarbonate, which is a base, is low. Having too little base is acidic. This is a metabolic acidosis without respiratory compensation. You actually don't even need all of the results from your BMP to figure out your acid-base status. So here I have a pH of 7.2, and I have a PaCO2 of 55, which is acidic. I don't have my bicarb back yet from the BMP, but it's possible that my bicarb could be very low or very high, and I could have some other acid-base abnormality going on. But I can actually figure that out just with the pH and the PaCO2 because I can calculate if the PaCO2 that is present is causing the pH to be as low as it is. And we do that based off of the Winters formula. Sorry, there's a lot of text on this slide. And based off the Winters formula, which is listed here but simplified, you can actually calculate how much your pH will increase or decrease based off the amount of PaCO2 that's around. So a normal PaCO2 is 40, and based off the Winters formula, your pH should increase by 0.08 for every decrease of 10 millimeters of mercury of PaCO2. And conversely, your pH should decrease, get more acidic by 0.08 for every 10 millimeters of mercury increase in CO2 over 40. So let's just apply that right now. pH is 7.2, PaCO2 of 55. Is that enough to account for my pH of 7.2? Let's take a look. First off, let's estimate how much the carbon dioxide alone should affect your pH. We know for every 10 millimeters of mercury, I should have my pH fall by 0.08. Well, I have 40 minus 55 millimeters of mercury means I have 15 millimeters of mercury additional CO2 than I should normally have. And I get 0.08 for every 10. So it comes out to 1.5 because it's 15 divided by 10 times 0.08. And that's, I should see a 0.12 decrease in pH based off that value. Well, a normal pH is 7.4, and I should drop by 0.12 from the amount of CO2 that's present. So if this was purely carbon dioxide influencing pH, I would only be at 7.28. And my measured pH is 7.2. That is lower than expected from the respiratory acidosis alone, which means that the elevated carbon dioxide does not explain the full reduction in pH, even though it does contribute to the acidosis. So there's another acid process present, and the only other thing that can be present is a metabolic process. And we could see this in other ways too. So here I have a pH of 7.35 and a PaCO2 of 25. Well, if we do these same steps, the same thing applies, right? For every 10-point fall or rise in CO2, it should impact pH by 0.08. So in this case, I'm actually 15 millimeters of mercury less than normal. My PaCO2 is 25 and normal is 40, which means 15 millimeters of mercury divided by 10, it's 1.5, and 1.5 times 0.08, well, I actually should have a 0.12 pH increase from having my PaCO2 this low. If it was just the CO2 playing a role here, my pH would actually go up to 7.52, and that kind of makes sense. It's what we've been talking about. This clearly is not a respiratory acidosis, and this is just kind of the math behind that, right? So I can see that the pH is 7.35, but if I calculate what it should be based off CO2, it should be 7.52. The pH is much lower than from the respiratory component, so something else is contributing, which must mean there is another acid process present, which is a metabolic process. So this is an acidosis that is definitely metabolic because I'm actually in a respiratory alkalosis. So this is metabolic acidosis with a respiratory alkalosis trying to compensate, and that's why the pH is 7.35. Let's look at another example, just quick, just getting lots of practice classifying these things. Here I have a pH of 7.2. That's acidic. My carbon dioxide is actually normal. All right. But my bicarb is 14, so that is a metabolic acidosis because my base is too low. That's acidic, and it's lining up with the overall acidosis in the blood. So this is metabolic acidosis without any respiratory compensation. And you can have any state of metabolic and respiratory acidosis or alkalosis superimposed on each other. Like this. pH 7.2, that's acidic, but I also have a PaCO2 of 79. That is acidic as well. And sorry, ignore the normal on the slide there. That's incorrect. And I have a bicarb of 14. That is also acidic. So in this case, I have a mixed picture, metabolic acidosis with a respiratory acidosis. So these all can kind of exist with each other. All you're going to do is categorize what you're looking at in order to understand the overall picture. So here's a quick summary of an ABG. They're helpful for determining a pH. You actually can also use a VBG to determine your pH. That's fine. They're also helpful to detecting some heme poisons if you're noticing a mismatch between your arterial oxygen pressure and your pulse ox saturation. They're useful to classify acid-base status overall into respiratory or metabolic acidosis and alkalosis, but they have limitations. Number one, your ABG uses a calculated bicarbonate, so you probably don't want to use that when you're trying to make your classifications. And even though they tell us if a metabolic acidosis is present, they do not tell us what kind of metabolic acidosis is present, which is very important. So now we're going to get into talking about things like anion gaps, and this is really relevant when we're talking about metabolic acidosis. So let's actually define what that is. Consider a metabolic acidosis as any time a bicarb is less than 20 on the basic metabolic panel. A gap acidosis is when you have that with an anion gap present. And a non-gap acidosis is when you have that without an anion gap present. To understand why this is so important, we have to understand some fundamental rules of physiology. So first off, you have never shot lightning out of your fingertips. You do not carry an electrical charge, and that is because there's a fundamental rule that says the positive charges in your body balance the negative charges. They are electroneutral. Let's look at the components of a BMP. I have sodium, potassium, chloride, bicarb, glucose, creatinine, and BUN. But let's get rid of the uncharged molecules, glucose, creatinine, and BUN. And that leaves me with my charged molecules. The positives are sodium and potassium, and the negatives are chloride and bicarb. Well, sodium is 140 and potassium is only 4. Since sodium makes up 98% of the positive charges I'm worried about, we're going to ignore potassium for now. But I promise the math works out if you want to include potassium too. So I have 140 sodium charges that are positively charged and need to be counterbalanced by negative charges in the body. Well, my negative charges are my 102 chloride and my 26 bicarbonate. But as you can see, there's still a significant gap. There's a lot of negative charges that must still be in the body. I'm simply not measuring them. And that's what the anion gap is. The anion gap is the unmeasured anions that I know must exist. I simply haven't measured them on a basic metabolic panel. And it's actually composed of things like albumin, organic anions, lactate, phosphate, and sulfate. So these are negatively charged particles that we don't routinely measure, but they have a contribution to charge. Also, many toxins are negatively charged, and when they're present in the blood, they contribute to that anion gap. So to understand why the anion gap is so important, we need to understand changes in bicarb in the body. So how bicarb moves around. And let's take a look at something here. So working with that concept of electroneutrality, we know that the total positive charges in our body must equal the total negative charges. And that means if one of these compartments changes, let's say a toxin gets added into the anion gap and increases by 1, well, then something else in that system needs to change so that there is another negative charge needs to go down by 1. So we have the same amount of negative charges. And it's certainly not going to be the chloride because you can't rapidly eliminate inorganic ions. Your body is not a nuclear reactor, right? So these won't be instantly created or destroyed. And it's also not going to be organic anions like lactate or phosphate because those need to be metabolized or cleared. You can't just poof those out of existence. So that leaves only bicarbonate, which can instantaneously change in this system because it is part of the body's buffer equation. So it can actually combine with hydrogen to become carbonic acid, and then turn into uncharged water and carbon dioxide and balance out our charges. So anytime anything in this system changes, the only thing that can instantaneously uh, adapt to create electroneutrality is bicarbonate. So that means there's several ways we can make bicarbonate go down, which is important when it comes to clinically assessing a patient. The first is increasing our inorganic chloride. So you could see here I have a chloride of 102, but if I were to drive that chloride up to 112, well, then there would only be 16 bicarbonate that would be generated in this system. I'm not going to remove any lactate or albumin, right? The anion gap won't change, only bicarb will. This is the most common cause of acidosis in the world, and it often occurs on day 2 of a hospitalization because a patient got 2 to 5 liters of hyperchloremic saline, which drove their chloride up. So even though their bicarb is low, I don't really care because it was all done from the fluids that we gave them. This can actually also happen from a relative decrease in your sodium compared to your chloride. So in this example, I have 140 sodium, which means I have 140 negative charges I need to balance it out with. But what if I only had 130 sodium, but my anion gap and chloride were the same? Well, then I still only need to generate 16 bicarb. So this is actually a hyponatremic non-gap acidosis. Okay, now let's look at an anion gap acidosis. So this is when I have an increase in organic anions that are increasing the amount of negative charges in my body. Let's use the example of lactate or lactic acid, which is a very, very common cause of this. So lactic acid acids like to get rid of hydrogen, so it'll deprotonate and become lactate, a negatively charged conjugate base. That lactate will then contribute to the anion gap, right? It's an unmeasured anion. So my anion gap is going to increase by 1 up to 13. So that means something else has to go down by 1. And luckily, that hydrogen it produced will combine with the bicarbonate. And if you remember Le Chatelier's principle from chemistry, when you add stress to a system at equilibrium, it will shift to relieve the stress. In other words, if I add substrate, I will drive to making more product, which would be water and carbon dioxide. And in that process, I'll consume a bicarb. So even though my anion gap increased to 13, my bicarb dropped down to 25. So it balanced out and I kept the same amount of negative charges. And if I were to do this 10 times over, a gap would go to 22 and my bicarb would go to, say, 16, right? Now, this is important. My bicarb is 16, but it's because my anion gap is 22. And there are many organic anions that are poisons and leave the anion gap elevated. So the mud piles mnemonic or cat piles mud, theophylline, aminoglycosides, methanol, uremia, diabetic ketoacidosis, alcoholic ketoacidosis, starvation ketosis, fenformin, all of these. You can go through the mud piles yourself. This is where we start to run into toxic alcohols, salicylates, lactic acid producing toxins like cyanide and carbon monoxide. All these things that we now need to start looking for because the labs are telling me there are some unmeasured anions that are causing problems. So because of that, it's really important to interpret the bicarb in context of all of the other electrolytes that predict it. So here is a tale of 2 bicarbonates. JB shows up to the emergency department after ingesting a full bottle of unknown pills 24 hours ago. He presents to the ED, asymptomatic, receives 2 liters of IV fluids, and then his laboratory studies are obtained. And here you can see his labs on the right. He's got a bicarb of 12. Oh no! They call you at the Poison Center and say, we have a significant acidosis. The bicarb is 12. You ask for your other things and find out his anion gap is also 12, and his chloride is 112. Well, you can see here that this is a metabolic acidosis driven by the high chloride. It's non-gap. This is hyperchloremic acidosis, and I don't really care because that's not a toxin-induced cause of acidosis. On the other hand, if JB shows up 24 hours after ingesting this with a bicarb of 12 because his anion gap is 22, well, a lot of things can cause the anion gap to go up. like salicylic acid deprotonating into salicylate, which will then increase the anion gap by 1 for each mole of salicylate. So this is an entirely different story. Yes, the bicarb is 12, but it's because his anion gap is 22. Now I'm worried and I need to start looking for different causes of that acidosis that are poisons, like salicylate, ethylene glycol, lactic acid, iron, all of these things. And this is why you should never call and just report a single bicarbonate. You need to know the chloride and the anion gap for this to be relevant in any way. Okay, so in summary, a gap acidosis is the presence of an anion gap greater than 20. And this means that there are some unmeasured anions contributing to the blood chemistry. We calculate it as a sodium minus a bicarbonate plus a chloride. That's your positives minus your negatives. And if that's greater than 20, you should start to think, something else is around. If you see that, it should prompt a workup for gap acid toxins, which you can remember via the mud piles mnemonic, which you will learn in other, hopefully in some other lectures. But you can refer to the previous slides if you'd like to see it. Now, for a non-gap acidosis, this is when you have a low bicarbonate, but a normal gap. It's usually from high chloride. There are a few toxicologic causes of this, but they're not super relevant. Things like toluene or bromine. This is usually not a toxic cause. And you can always call and ask for more information from the toxicologist on call, but it's very rare that this is a toxic cause. Okay, since we're talking about gaps, we also have to talk about osmolar gaps. And to talk about osmolar gaps, we need to know what an osmole is. And to know what an osmole is, we need to know what osmosis is. So osmosis is the movement of water following water's concentration gradient, going from high water to low water concentration. In other words, going from low solute, which you could see here on the right, to high solute, which you could see on the left, where you have more solute per water. So an osmole is any solute in solution, so anything that's dissolved in water. And what contributes to osmolarity in the body? Well, everything that is dissolved in the serum of the body. So we have our charged molecules and our uncharged molecules. If we want to calculate the contribution of our charged molecules, well, hey, remember our positives equal our negatives? If you take 2 times sodium, that roughly accounts for all of the charged molecules because we know sodium is the predominant positive charge and everything else matches the amount of charges sodium contributes. And then our uncharged molecules like glucose and BUN, well, I need to know how many of those are dissolved in the blood. And because osmole is referring to how many moles of solute are in solution, I need to calculate the moles of glucose and BUN. So if I want to calculate my osmolarity, it's simply 2 times sodium to deal with all the positively charged substances and negatively charged, plus glucose in moles and BUN in moles. So the conversions for that are 2 times sodium plus glucose divided by 18, which is a conversion factor based on its molecular weight, and BUN divided by 2.8, which is the same thing. So why don't we practice? I'll encourage you to take a look at this basic metabolic panel, pause the video here, and calculate the calculated osmolarity. When you're done, press play and I'll go through the answer. Okay, so we have 2 times our sodium, which is 140 times 2, or 280, plus glucose over 18. 180 divided by 18 is 10, and BUN divided by 2.8. 28 divided by 2.8 is 300. That is my calculated osmoles of 300. That is when I'm measuring everything in the blood. If that is all that's contributing to osmolar force, my osmolarity should be 300. But if I then measure my osmolarity, and it is much higher than that, like 340, it means there must be some other solute in the blood that I have not measured. So this is where the concept of an osmolar gap comes into place. An osmolar gap is your measured osmoles minus calculated osmoles. In this case, 340 minus 300 is 40 milliosmoles. So, what is that gap? Well, they're unmeasured osmotically active substances that clearly we weren't able to put into our calculations. And in toxicology, this is most often toxic alcohols like methanol, ethylene glycol, or isopropanol. But other things could contribute as well, like ethanol or acetone, which is a ketone sometimes seen in DKA, propylene glycol, which you can find in drugs, mannitol, or even radiographic contrast if it was recently administered. So, overall, osmolar gaps are useful to identify unmeasured solutes, or also known as uncharged toxins. Usually, charged toxins like salicylate we'd pick up in the anion gap. But if they're not charged, like an alcohol, we have to pick them up in the osmolar gap. This is, however, relatively limited, and it's important to be aware of the limitations. There are many different equations that are used to calculate serum osmolality, and there can be significant variability in the calculated osmolality that you get, depending on which equation you use. Because of that, you can get serious variation in the actual osmolar gap, meaning the calculated minus the measured, if you're getting different values for your calculated. So, an elevated osmolar gap may support the presence of a toxic alcohol, but a normal osmolar gap does not rule it out because you might have used an equation that doesn't give you a very big gap, or it could be a small ingestion that actually doesn't reliably produce a significant osmolar gap. So you can use this to support a diagnosis, but you cannot use it to rule out the diagnosis of toxic alcohols. Okay, that takes us to the end of our laboratory assessment for ABG, anion gaps, and osmolar gaps. Next, we're going to talk about calculations. These are really, really important to know for the SPY exam. And there are some constants that you're likely going to want to know. The first are proportions or percents. So on the left here, you could see percent. And percent means per 100 because cent is the Roman for 100. You're going to want to know what the different percent weight by volume, and volume by volume mean. And unfortunately, you kind of just have to memorize these. Weight by weight is how many grams per 100 grams. For example, 5% weight by weight would be 5 grams per 100 grams. Weight by volume is how many grams per 100 milliliters. For example, 5% weight by volume is 5 grams per 100 milliliters. And then percent volume by volume. So this refers to how many milliliters per 100 milliliters. So if you can remember those, you'll be in a good place to do the appropriate calculations needed for the SPY exam. Other things that are important to know are things like density, which is the weight of a liquid per volume. And this helps us when converting a volume of a liquid to a dose in weight. You multiply the volume of the liquid by the density. We'll practice doing this in a minute. The other conversions that are really important to know are conversions from standard US measurements to metric measurements. For example, a fluid ounce is 29.6 milliliters. There are 8 ounces to a cup, 2 cups to a pint, 2 pints to a quart, and 4 quarts to a gallon. You might need to calculate how many milliliters are in a gallon, and you would have to convert back to ounces in order to figure out milliliters. You'll need to know weights. For example, 28.5 grams per ounce, 16 ounces to a pound, and very importantly, how many kilograms to a pound, or how many pounds to a kilogram. And your metric conversions. There's 1,000 milliliters in a liter. There are 10 deciliters in a liter. So working your way through these different conversions is important. And unfortunately, you simply have to memorize the US equivalents, because other than quart to a gallon, there's 4 quarters to a gallon. None of them make a lot of sense. Uh, and use those conversions when you're making your conversions and your calculations. So we'll do some practice problems here. Because on the SPY exam, you're going to be expected to convert between pound and kilogram patient weights to calculate the total drug dose in weight that was ingested from a volume ingested and to calculate ingestions in doses per kilogram. So we'll practice a few of those here. Let's start with determining the dose of something ingested from a percent strength product. These are actually really simple if you recognize the proportion will never change, only the volume that was ingested. And if you remember that percent means per 100, it's an easy way to remember how to start these out because you can always use this equation. Your percent divided by 100 is equal to X, which is what you're solving for, divided by whatever the new volume is in the actual question that's asked you. Let's use the example. How many grams of lidocaine are in 29 milliliters of 4% weight by volume lidocaine? Well, if you remember, weight by volume, you can go back a few slides, is grams per 100 milliliters. We can set up our equation. 4 grams divided by 100 milliliters is equal to X over 29 milliliters. Now, I'll divide my 4 by 100 to make this easier, and I'm actually left with a density. I have 0.04 grams per 1 ml of this lidocaine solution. And I'm solving for how many grams are in 29 ml. Now I'll just multiply 29 on each side to solve for X. My milliliters will cancel out, and I have 29 ml times 0.04 grams per ml, which leaves me with 1.16 grams in 29 milliliters of 4% lidocaine. The other thing you're going to need to do are conversions between units. So when you're doing this, just remember, set up your equations so the final product that you want, when you're doing this, set up your equations so the desired final unit you want your product in is on top. And you can use the conversion constants from the previous slides to set things up. Let's take some examples. Convert 5 kilograms to pounds. Well, your final product should be in pounds. So I know I have 2.2 pounds per 1 kilogram, and I'll multiply that by 5 kilograms, which is also on top. My kilogram on top and kilogram on bottom will cancel out, and that means 2.2 times 5 is equal to 11 pounds. Or you might need to convert ounces to milliliters. Well, I want to end in milliliters, so let's make sure that's on top. There's 29.6 milliliters in 1 ounce times 3.4 ounces. If I multiply the two, my ounces will cancel out, and I have 29.6 times 3.4, which equals 100.64 milliliters. Many of you may say, well, I use 30 milliliters or an ounce, or 29.5 milliliters to an ounce. And we'll go back just to look at this. It doesn't matter what you use. Apologies. There likely will not be a question where if you use 29.6 versus 30, you're going to get it wrong. The answers will be significantly different enough that you could use either one of these interchangeably and you'll still get a answer within 1 or 2 milliliters of each other. It's unlikely they're going to try to trick you there. Okay, try an actual case. Here we have an anxious parent who calls the poison center about her 2-year-old that drank 2 ounces of Scope mouthwash. That's 49% volume by volume standard density alcohol. If the child weighs 31 pounds, how much pure ethanol did she ingest in mils per kilo? Well, let's start off by getting to kilograms from her weight. So to do our weight conversion, I want to end in kilograms. I'll make sure that's on top. 1 kilogram per 2.2 pounds times 31 pounds. My pounds will cancel out. 1 divided by 2.2 times 31 equals 14.09 kilograms. Next, I need to know the total milliliters she ingested, which I have to derive from this proportion of 49%. And I know that percent is in milliliters per milliliter. So I need to get my ounces into milliliter. So let's do the volume conversion. Ounces to ml, 2 ounces times 29.6 milliliters per ounce. My ounces will cancel out, and I have 2 times 29.6, which is 59.2 ml. Now I can do my proportion. 49% volume by volume means 49 milliliters per 100 milliliter. So 49 divided by 100 is equal to X over my new volume, which is 59.2. If I do the math there, shows me I have a density of 0.49 milliliters per milliliter. And to solve for X, I'll multiply 59 by that. And we will get our answer of 28.91 milliliters of pure isopropyl alcohol that was consumed. Now, to get that, or sorry, not isopropyl, ethanol. To get that into milliliters per kilo, it's simply 28.9 milliliters of ethanol divided by 14.09 kilos of human, and I get 2.05 mil of ethanol per kilo. Let's try another example here. I don't know why there's a Tylenol there, but this is a babysitter watching TV. Okay, let's try another example. A babysitter was watching TV, and during the commercial, she found that Susie was in the bathroom with an open bottle of rubbing alcohol, 70% volume by volume. The container was 16 ounces when it was brand new, and there's only 12 ounces left. If Susie weighs 54 pounds, how many milliliters per kilo of pure isopropyl alcohol was ingested? Very similar to our last question. So let's start off by calculating our weight, which we know 54 pounds times 1 kilogram per 2.2 pounds is equal to 24.5 kilos. Now let's get our volume. 16 while new and 12 ounces remain means 16 minus 12 is 4 ounces that were removed. Just a reminder, you can actually pause this right now and try to solve this yourself and then resume it, and I'll go through the answers with you. So 4 ounces, I need that in milliliters. So I have 29.6 milliliters per 1 ounce. That leaves me with 118.4 milliliters to do my proportions with. I know I'm 70% volume by volume, which is 70 milliliters per 100 milliliters of total solution, or isopropyl alcohol. And I'm going to multiply that by the 118.4 milliliters that this child potentially ingested. That means out of that 118.4 milliliters, 82.6 mLs were isopropyl alcohol. So isopropyl dose in milliliters per kilo would be 82.6 divided by 24.6 kilos, which gives me 3.35 mils per kilo. Now they might actually give you the density and ask you to calculate in milligrams per kilo. So what is the dose in milligrams per kilo that they ingested if the density of isopropyl alcohol is 0.785 grams per milliliter? Well, I already calculated the exact amount of isopropyl alcohol milliliters that was in that total amount of milliliters she ingested. So let's convert to grams. I'll say there's 0.785 grams per milliliter of isopropyl alcohol, and I calculated Susie ingested 82.6 milliliters of pure isopropyl, which is 64.84 grams. And let's say they want this in mgs per kilo, though. So I now need to convert grams to milligrams. So ending in milligrams, I'll make sure I have 1,000 milligrams on top per 1 gram times 64.84 grams. My grams will cancel out. I have 1,000 times 68.84, which is 64,840 milligrams. So my isopropyl dose in mgs per kilo is 64,840 milligrams divided by 24.5 kilograms of Susie to get 2,646 milligrams per kilo. Now, right here, I have 3 practice questions that will help you practice doing conversions and proportions. I want you to stop the recording here, practice these questions, and on the next slides, I'm going to show you the answers. So go ahead and pause now. Okay, let's take a look at our answers. Here are the steps to solve the answer to question 1 about the 2-year-old who ingested 12 ounces of 5% volume by volume ethanol, who weighed 22 pounds, and they gave you the density of ethanol. You can go through each step here and pause it if you'd like to read more. However, you might have found slightly different answers depending on what you used for your ounces to milliliters, whether it was 29.6 or 30. Like I said, when they give you a multiple choice answer on the SPY exam, it's likely going to be significantly different between the answers where you won't get it wrong for choosing the wrong conversion factor. But these are the steps that you can go through. Feel free to pause if you'd like to read them longer. Our next is the 30-pound child who ingests half of a 1-gram bar of 0.01% bromethylene weight by weight. You can see via these steps, they ended up ingesting 0.05 milligrams of bromethylene or 50 micrograms of bromethylene. And you can pause if you'd like to go through each step here. And finally, we have our 5-year-old child who ingested 3 ounces of 3.2% weight by volume acetaminophen, which, if you did the math, you would notice that that's 32 milligrams per milliliter or 160 milligrams per 5 ml standard acetaminophen concentration. Just a fun way to show that these are just different ways to express concentration. The steps are all there, so feel free to pause and go through each one. Remember, slight rounding differences between us might have gotten us slightly different answers, but it's not going to be significant on the exam. Okay, feel free to go through and review these different labs and calculations again in order to practice the conversions and proportions, which will be really helpful for you on the exam. And I hope you learned a little bit about the different ways we interpret labs and how we can use some math to help figure out what kind of danger a person might be in after an ingestion. Thanks.